In Chapter 7, we're going to revisit waves, but this time we'll talk specifically about light. Light is a transverse wave. Transverse waves, like we learned about before spring break, are waves that propagate or move perpendicular to their motion of oscillation, so that they have an up and down sinusoidal shape as they propagate this way through space. Like sounds, we can categorize light on the basis of either wavelength or frequency, and we can split up distinct regions of wavelengths and frequencies for light waves as part of an overall electromagnetic spectrum. In this electromagnetic spectrum, we give names to particular regions of light depending upon their wavelength or frequency value. At very small wavelengths or very high frequencies, at one extreme of this spectrum, we have gamma rays. At the opposite end, very large wavelengths or very small frequencies, we have radio waves. So on the left-hand extreme, our wavelength is small, so lambda is small, and our frequency is big, f is big. At the opposite extreme, those two things swap. Lambda, our wavelength, is large, and frequency is small. We'll revisit what these quantities mean in just a few moments. First, though, recognize that in the center of this spectrum, a very small sliver of it is dedicated to visible light. Our eyes are particularly puny detectors of light. We can only see this small sliver of the entire electromagnetic spectrum, from a wavelength of about 400 to about 750 nanometers, or frequencies from about 4 times 10 to the positive 14th power to 7.5 times 10 to the positive 14th power hertz. This visible region contains colors that we can detect even within this small sliver, from red on the right hand, large wavelength, small frequency extreme, to blue and purple on the small wavelength, large frequency extreme. Generally speaking, this visible spectrum of light has wavelength ranges and frequency ranges, shown here, that specify colors that we can classify as red, orange, yellow, green, blue, and indigo/violet. All told, we can remember this order of visible light by the first letters of this sequence: R, O, Y, G, B, I, V, or Roy G. Biv helps us remember the order in which visible light is patterned. At one extreme of visible light's spectrum, the red extreme, wavelength is large and frequency is small. So over here, wavelength is large and frequency is small. At the opposite extreme, the violet end of the visible spectrum, wavelength has become small and frequency is now large. So wavelength decreases from red to violet, frequency increases from red to violet. So let's review wavelength and frequency from back in our sound chapter. For light, we can describe light on the basis of wavelength and frequency, and also on the basis of energy. Light is an odd substance. It sometimes acts like a wave and sometimes acts like a particle. In fact, the sometimes occur simultaneously. In a few moments, we'll talk about the behavior of light as a particle when it acts like a photon of energy. But first, we'll review the wave characteristics of light. we discussed wavelength as the distance between successive wave crests for light waves, or for any wave for that matter. A wavelength is the distance from one peak to the next, or the amount of length that's swept out by one complete wave cycle, which is one trip up and one trip down, or one crest and one valley. For light, because these wavelengths are small, we often give units of nanometers. Frequency, meanwhile, is the number of wave cycles, again, one crest and one valley, that we would count moving past a given point every 1 second. The units of frequency may be cycles per second, or inverse seconds, 1/seconds, also called hertz and abbreviated HC. We mentioned back in chapter 5 that light travels with a constant velocity under constant conditions. The velocity of light, how fast it travels, with units of meters per second, is a universal constant in a vacuum, 3 times 10 to the 8 power meters per second. The relationship between frequency, speed, and wavelength for light is therefore a constant value. So, our speed of light gets a special symbol. Because it's constant, we'll give it the symbol c. And that speed, like the speed of other waves, is equal to the wavelength of light times the frequency of light. So, once again, lambda, a Greek letter that looks like an upside down Y, is our wavelength, which must be given in meters if it's not already. F, frequency, in hertz or inverse seconds. Remember that 1 meter is 1 billion times larger than a nanometer. So that 1 meter is worth 1 billion, or 1 times 10 to the 9th power nanometers. Suppose, for instance, that we'd measured a light wave with a wavelength of 560 nanometers. What would its corresponding frequency be? And what color would we perceive that light wave as? To answer this question, we're going to need to take advantage of this relationship between the speed of light, wavelength, and frequency. The speed of light is a given constant. Here, we've measured a wavelength and need to calculate a frequency. So let's do so. Our wavelength is given as 560 nanometers. We know that there are 1 billion nanometers in 1 meter, so a nanometer must be a smaller overall quantity than meters. To get from nanometers to meters, we'll need to skip a decimal point to the left 9 total times. That allows us to say that this is 1, 2, 3, 4, 5, 6, 560 meters, or 5.6 times 10 to the minus 7 meters. We make this conversion because our speed of light, c, is a constant whose units are in meters per second. It has a value of 3 times 10 to the 8 meters per second. And that speed of light is equal to wavelength times frequency, or frequency is equal to speed of light over wavelength. We know our speed of light as a constant. We know that's equal to wavelength here, 5.6 times 10 to the minus 7 meters times frequency. To solve for this thing, divide both sides by it. The right-hand side goes away, and on the left, our units of meters cancel. So we're just left with 1/seconds, which is the same as hertz. And the frequency in hertz is given as 5.36 times 10 to the positive 14 power. So make sure that you can replicate this type of calculation yourself and plug in numbers here appropriately. Finally, if we refer back to the previous page, what we'll find is that this wavelength of 560 nanometers, or frequency of 5.36 times 10 to the 14 hertz, corresponds to a color that's green, regardless of whether we refer to wavelength or frequency. We verify that this must be green light. All right, so now let's do one more thing here. When we talked about waves for the first time, we said that waves transport energy. Light is a wave and it transports energy. When we think about light waves transporting energy, we think about that energy being packed in the form of a particle called a photon. Photons are like little packets of energy. A photon is a packet of light energy. Albert Einstein won the Nobel Prize for identifying the photoelectric effect. That light of a particular frequency can produce electrons from a particular material. If light is capable of doing this, then it must be capable of transferring some of its energy to matter. The energy that light packs is determined wholly by the frequency of a light wave. How many wave crests or cycles can be counted moving past a point per second. The energy of a photon, the energy of one packet of light, given the symbol E, is determined by Planck's equation. Planck's equation looks like this. E is equal to h times F. In this equation, E is energy, F is frequency once again, given in hertz. But H is a new constant. Again, it's a given constant, but it's a fundamental physical constant of the universe. It's called Planck's constant. Planck's constant has a value of 6.626 times 10 to the negative 34th power, with units of joules for energy times seconds. So this is joules times seconds. To calculate the energy of a light wave, or the energy that it packs, we need to know the frequency of that light wave. So let's calculate the energy of the light wave that had a wavelength of 560 nanometers. A few moments ago, we found that that wave had a frequency equal to 5.36 times 10 to the 14 hertz. The energy of this same light wave would be equal to Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, times the frequency, 5.36 times 10 to the 14 hertz. In this equation, because hertz is the same as 1/seconds, seconds and hertz cancel each other out. The energy of this wave, therefore, in joules, ends up as 3.55 times 10 to the negative 19th power. And when calculating the energy of a light wave, we'll often find that it falls in the range of something times 10 to the minus 19 joules. So let's add our exploration of energy dependence onto this slide. Earlier, we said that at one extreme of the electromagnetic spectrum, the gamma ray extreme, wavelengths are small, frequencies are big. Because energy is equal to frequency times a constant value, when frequency is large, so too is energy. So that on the gamma ray extreme of this electromagnetic spectrum, energy is big when frequency is big. And at the opposite extreme, when frequency is small, energy is likewise small. Radio waves have low energy, gamma rays have high energy. In fact, as we move from right to left across this spectrum, energies get larger and larger. And at the left-hand extreme are large enough to break chemical bonds like in the DNA that makes up your body. In the visible spectrum, Roy G. Biv, down here, when frequency is small, energy is small. The red-hand extreme of the visible spectrum is smaller energy light. And the violet extreme is larger energy light. Energy is higher for the blue and violet end of the electromagnetic visible spectrum than it is for the red and orange end. Similar to the ways in which sound waves reflect, we can also think about light waves reflecting, refracting, and generally bending as they travel and encounter obstacles. Light waves bend by diffraction when they travel through a small slit to create a pattern of alternating bright and dark spots as they constructively and destructively interfere with each other in turn, either in phase for constructive interference or out of phase for destructive interference. Constructive interference results in an amplification or brightening of waves. Out of phase destructive interference results in the destruction or darkening of waves. Refraction, on the other hand, is the bending of a light wave as it moves specifically from one medium into another. Suppose, for instance, that we were going to shine some light into water. Light that hits the water surface might come in like this. But as that same light travels through water, it might bend to skew to look something more like this. So as light travels from one medium, say air, into another, like water, it bends, it changes course. You've seen this in action if you've ever placed a straw in a glass filled with water and looked at it side on. Perhaps you've seen something that looks like this picture. The amount of change, how sharply this wave bends as it passes from one medium into another, is dictated by the refraction index, or index of refraction for a material. All materials have some index of refraction. It tells us how sharply they will bend light compared to another medium. This index of refraction, given the symbol lowercase n, is the ability of a material to bend light. This is a unitless quantity and is relative to a vacuum where there's absence of material. In a vacuum, the index of refraction is 1. To a good approximation, the index of refraction of air is likewise about 1. As light travels through a vacuum or through air, it is seemingly undisturbed in its course. But as light hits another medium, like water, it seems to bend. This phenomena in bending as light travels from one medium to another is due to a change in light's speed as it moves into more and more condensed phase materials. Similar to the way in which sound's speed can change, as sound moves through different materials, so too can light's speed change as it moves through different materials. The speed of light in a vacuum is a universal constant. That's c. That's 3 times 10 to the 8 meters per second. But this is only true in a vacuum of space, and to a good approximation, it's also true in air. As light moves through more condensed phase materials, like water, for instance, its speed changes, though. That change in speed, or the new speed of light through a material, the velocity of light in some new material, is determined by the speed of light in a vacuum, that universal constant, divided by the index of refraction of a material. The new velocity v, the speed of light in a new material, given in meters per second, is equal to that universal constant in a vacuum, the speed of light, 3 times 10 to the 8 meters per second, divided by the index of refraction of material that light is traveling through. For example, water has an index of refraction of 1.33. Let's calculate the speed of light moving through water. In order to calculate this new speed of light, we take advantage of that equation up above and say that the new speed of light, v, is equal to the speed of light in a vacuum, the constant 3 times 10 to the 8 meters per second, divided by the index of refraction of the substance that the light is moving through. Here, water has that index of refraction, 1.33. Divide 3 times 10 to the 8 by 1.33, and we end up with 2.26 times 10 to the 8 meters per second. Light has slowed down moving through water, and so it appears to bend. One last phenomenon that we can discuss with regards to light's behavior as a wave is reflection. We discussed reflection to a small extent when we talked about sound waves and echoing. Reflection for light waves means a rebounding of light from a surface. When light reflects, it rebounds away from a surface and occurs at an angle that's equal to an incident value or original value. For example, if we shine light at a mirrored surface, like I'm trying to illustrate in this gray block here, where light comes into the surface like this, say at an angle of 45 degrees with respect to some imaginary straight line that we can draw right down the middle. We would expect light to bounce off of the surface or rebound away from it at an angle that's equal to that incident angle. So we call this wave the incident wave. It's incident upon a surface like this mirror. It's the original incoming wave. Reflected light will come off of this surface at an angle that's equal to that incident value. So this is reflected light. And the angle with which it leaves the surface is the same as the angle with which it hit the surface. Here in this example, it's 45 degrees. In the laboratory this week, we would have investigated the reflection and refraction of light, but in lieu of a physical experiment, I've set up the simulation for us to look at. This is accessible via your course Moodle page. What I'd like you to do is look at the intro experiment. In this experiment, we're going to shine a light wave on the surface of a material and watch it reflect off that surface and refract or bend as it moves through that surface. So, I'm going to keep this material in the outer white portion of the simulation air. And the inner portion, we're going to choose as either water or glass. We'll start with water first, so we'll leave it at its defaults, just like it is right now. We'll turn this light on and watch what happens as Laser light, this red light, is shown at the surface of water. We'll see that some of that light reflects off the surface and bounces away at an angle that's equal to the incident angle. If we measured those angles like we would have done in the laboratory this week, we could have set the incident angle or the incoming angle at whichever value we chose. Maybe here, for instance, I'll choose to input at 60 degrees with respect to this vertical line, that's dashed line, through the middle of this picture. What we'll see is that light reflects away from the surface of water at 60 degrees, the same angle at which it came in. But light refracts or bends as it moves through that water at an angle that's much different. This angle that light refracts at is based upon the index of refraction of this material, namely water here. As we change that material, we change that index of refraction. Glass, for instance, has a different index of refraction, and so it bends light more sharply. Notice that there's a more drastic change in how light is bent moving through glass, where this angle down here in the purple material is now 30 degrees to the right of this vertical dashed line, whereas in water, it was closer to 35 or 36 degrees. What I would like you to do is to use this simulation to mock some of the material from the experiment involving reflection and refraction through materials. And think about how you can answer some of those questions in that laboratory exercise using this simulation.